Thank you for the introduction. My name is Zhang from CMU. Today I'm really happy to be here to present our work on sensing posture-aware pen-and-touch interaction on tablets. This project was done in collaboration with my colleagues at Microsoft Research and the product team advised by Hinckley. As we know, the mobility of tablets makes them ideal to be used in many different contexts, such as user working in front of a desk, or sitting on a couch sketching some ideas, or writing while walking to get some last-minute work done before class. As we can see, in all these contexts, users grab the device differently and change their postures all the time to support their interaction with the tablet. But traditional UI forces the user to always reach for the widget at fixed locations, which is more like a device-centric approach. So we wonder, can we design better tablet interactions that leverage and adapt to user postures, such as the mobility, the screen angle and orientation, the handedness, the hand direction, and the occlusion because the hand hovering above the screen, the position of the gripping hand, as well as the reachability of the thumb. So we want to do something to shift from a device-centric approach to more of a user-centric approach. To illustrate the goal of this work, let me draw a chart that reflects the common tablet interactions, from which we can see a degradation. So on the left side, we have rich user posture information, and due to the limitation of tablet sensors, not all of them can be sensed. And down to the end of the chart, here we have existing tablet interfaces, which are mostly device and word-centric, knowing little about user postures. So this work targets user-centric frames of reference, which we aim to bring interaction to the users rather than forcing the users to adapt to interactions. We further break this down into 5 different frame of references, which I will show with examples later in my talk. To achieve this, we first build a set of custom hardware and software to sense the user postures. Then we explore different interaction scenarios where our posture-aware interfaces morph to a suitable frame of reference at the right time for the right posture. Here, I will show a quick preview of what we built in this project. Our posture-aware UI knows when the tablet is picked up by the user and comes closer to the gripped edge, so it's reachable for the thumb. It follows the planted palm on the screen, which preserves the palm position during some fine-grained drawings. It can also be summoned by an explicit touch gesture. Note that the widget knows which direction to project to and avoid hand occlusion. And it also knows when to disappear and when to stay on the touch screen based on the availability of users' hands. Now let me first talk about the hardware and sensors we used in this project. To sense beyond the touch screen, we built a self-capacitive sensing electrode ring, which we can see here. We attached this bezel to the top screen bezel of the Surface Book. This electrode ring has 52 electrodes. Each measures 10 by 15 millimeters with a thickness of 0.4 millimeter. This electrode ring is then connected to a customly built sensor board, which features 4 analog device capacitance sensing chips and a 120 megahertz microcontroller with Wi-Fi connectivities. Here is a picture of our tablet prototype. In total, there are 3 sensor signals we leverage in this project. The first one, as I mentioned before, is this screen bezel electrode ring, which projects a peripheral electric field around the device. This allows us to sense the proximity of a user's hand up to 20 centimeters above the screen. And second, we use the screen capacitive image. This gives us a rich contact information, such as user's palm on top of a screen, rather than merely giving us the touch location. And third, there's a IMU sensor, including the accelerometers and gyroscope, which we use to get the device angle and orientation. So these 3 signals work synergistically to reveal the posture information of a tablet user. Here's a short video that shows the signal we use to detect user postures. The height of the bar on the screen shows the capacitance change, as you can see. And also the center, the white blob, are the footprint of my palm. So as you can see, the signal change dramatically when I hold and grab the device differently when I'm drawing something. They all appear differently from a signal point of view. Using the same set of hardware, we can also sense the hand hover signal, which we use to track the user hand direction on touch events. Here, let me show some interaction techniques based on this postural awareness. We use the color palette in a drawing app as one example of a wider range of applications that can benefit from postural awareness. So on the screen here, we can see the different shapes which the color palette morphs into for a suitable user posture. Our first example is a set of tools manipulated by user's thumb of the gripping hand, which have already shown some high promises in prior work. Our postural-aware thumb tool comes to the gripped edge with the device when the device is picked up by the user. As you can see here, I can tap on the thumb tool to change the color of my pen. I can also click on the marking menu to expand the selection of controls. The thumb tool follows the gripping hand, so it is always reachable by the thumb, regardless of the device orientation and the gripping location. Sometimes it is ambiguous to the sensing system when the user grabs the device with both hands. So in this case, we allow the user to make a selection by slightly tilting the device, which could be natural and implicit. The thumb tool also changes its transparency according to its distance to the gripping thumb for being less intrusive when it is not needed. Our second example includes a set of palm tools which follows the user's palm, allowing the user to get quick access to controls without losing his or her position during some fine-grained drawing tasks. Here we can see the palm tool updates its position at the touchdown event of a user's palm, and it fades away when the user rolls the palm to the back. Here is a close-up of the palm tool fading away and solidifying according to the position of a user's palm. So our palm tool also takes advantage of what people often call a muscle memory. Since the palm tool rotates together with the user's hand, the true north is always consistent regardless of the user hand direction. So a swipe to the north gesture always triggers the action the user would expect. Our third example is a set of fan tools summoned by two-finger explicit touchdown gesture. This fan tool always projects itself to the opposite direction of the hand to avoid occlusion. It disappears at the finger lifting up and stays on the screen when it senses the non-dominant hand is busy grasping the device, like it's now. And it waits for the triggering hand for the action. Posture awareness can also benefit tangibles on tablets. We found that tablet users often have a hard time understanding the functionalities of the pen. In other words, it's not very discoverable what a eraser button can do and what the barrel button can do. So we built this app where the user can put their pen down on the screen to reveal their functionalities. We know that tablet screens are often tilted, being too slippery to hold the tangibles on the screen. In response, we enable an imprint mechanism, putting the pen down on the screen, imprints itself, and leaves a phantom as its proxy when the screen is tilted. So as you can see here, I can use the barrel button and the eraser to copy and paste the different things I draw before and do a swipe up to exit the imprinting mode. We can also use the pen as a container to save user context. For example, here, I imprint on the left margin and to save some images for later use. We also leverage posture awareness to create a smart auto-rotation. The most related previous work, I-rotate grasp, uses absolute grip gesture to predict phone screen orientations. On a tablet, we noticed that users always change their grip when they want to rotate the screen, but not that much when they don't want to rotate. So we implemented this smart auto-rotation by simply disabling the default auto-rotation when the user's grip doesn't change. So now I'm changing the grip so the screen rotates accordingly. So and it avoids accidentally rotate the screen when I just like lay down without changing my grip. We run a user study to get some feedback from the users with 8 participants, and they all used tablet before, they all used active stylus before. For the thumb tool, people found the animated transition between the default position and the various of different user-centric UI positions was very important for them to understand what was going on. However, it's very interesting. We found some participants intentionally repositioned their gripping hand just to move around the thumb tool, which suggests that our background sensing technique actually was sometimes used as a foreground gesture input when the interaction becomes more obvious and understandable to the user. So for the palm tool, we found people suggest that this tool is useful because it minimizes the hand and pen movement. It helps maintain the previous status for both hand and attention. It helps them to stay focused on the current task. However, we found some participants noted that the solidified menu gets in the way of where the user wants to draw. This suggests a further use of transparency or some logic that leverage the underlying content might be also be helpful to mitigate this problem. So for the fan tool, people like the smartness. When they see the fan knows when to stay, when to disappear. It is especially useful for mobile platforms such as phones and pad when they tend to switch hands a lot. And interestingly, some users interact manually, which means they only interact with the menu with just one hand, regardless of the availability of their hand, which suggests a few future refinement based on both the hand availability and the handedness. So for the tangible pen tool, people found the phantom pen is very important. They make the interaction more stable and more visually understandable. So to summarize this work, we propose using posture as a seen but unnoticed aspect of tablet interaction and can be leveraged to create new experiences. We broke this user-centric approach into many contextual nuances, particularly in terms of sensing, body, arm, hand, pen cursor, and grip-centric frame of references, as opposed to forcing the user to work with device-centric tablet UIs. We built our sensing technique based on pragmatic combination of 3 sensors. It is practical because our bezel sensor only requires minimum instrumentation to the existing device, and the 2 other devices are already built in consumer tablets. We built our sensing technique. Finally, we implemented all interaction and then conducted user study and then collected some preliminary user feedback, which shows some high promises of this work. So I want to conclude my talk with some future work we aim to do. First, we want to explore the possibility of sensing and leveraging other types of user postures information, such as a gaze or grip force or even a full body posture that better infer the context of a user using tablet. We also anticipate that other than the tablet, there are many other form factors such as wearables or larger devices which could benefit from our sensing and posture awareness. Finally, we need to study in more depth the trade-off between the fine-grained constant UI adjustment and versus the animated transition between a few simple states. We found during our early design study that a constant adjustment of UI could be annoying. So our final design took this into account and make the UI feel more stable and predictable. This could be a trade-off, and it could worth future studies, which we plan to do in future. Okay, with that, I would like to conclude my talk. Really, thanks everyone for your attention, and I'm happy to answer questions.
Cool, thank you. That was interesting. Does anyone in the audience? Okay, could you just say your name and affiliation?
Yep.
Thanks.
Fabrice Matulik, preferred networks. Can you hear me?
Yes, I can.
I know some people have. It's a bit difficult to hear. So great work. I see a lot of the techniques here. There's a lot of prior work on grip sensing and posture-based menus and pen interaction, you know, and a lot of it done by Ken, actually. So I was wondering, what is the, in your opinion here, the distinguishing feature of your work? What is the, let's say, the most novel tool of your interface compared to all that prior work? Because from what I see, like the phantom pen seems to be pretty novel, but the rest, I feel I've seen in a lot of prior work on tabletops and tablets, and a lot of it by Ken. Yes.
That's a great question. And actually, in the paper, we did acknowledge a lot of prior work. I actually did a survey type of table that basically group all the previous work that we thought are relevant. Many work are from Ken, and then position our work among the previous work. Actually, I will give you one example. So the thumb tool was originally from Ken's group, but they always assume the position of the user's grip hand. So it's still like, it is useful, but sometimes you don't really know what is the best posture user might want to do with their tablets. You cannot simply just assume that they will always grip the same location every time. So now with our technology, including the sensor that I built in this product, we finally have a tool to infer the location and such information to do a better job to adapt to users' posture. Especially, we found that users tend to change their posture to avoid, fatigue, and in different mobility levels. So they tend to switch postures a lot. And I think part of the core contribution is the sensing technology, and also the investigation on how to combine practical sensing technologies to better infer user posture to improve based on previous work.
Thank you. Interesting talk. I'm a big fan of the pen-centric computing. I have a couple of areas of question I was wondering if you were working on or had any data on. One is false alarm rates for some of these different capabilities, and also what is your strategy for minimizing false alarms. The other is user testing, where people are engaged in situated tasks, and whether you've evaluated the cognitive load of the continual adaptations that they're experiencing as they work, and what the impact is on performance.
Thanks for the question. For the first question, is the false alarm same as false positive? For example, like I detect the sensor detects user grip at one location, but actually the user is gripping at another location. By false alarm, do you mean false positives?
By false alarming, I mean that the interface itself completes an adaptation which was not the user's intention. So instead, it is experienced as a disruption.
Yeah, actually, in our early design, we did find sometimes we overly optimize for user postures, and that could be annoying. Give you one example is the palm tool. In our early design, actually, we control the palm tool to always, like a puppy dog, always follow the user's palm no matter where they go. And we did some study on this early prototype, and people found it's just really annoying because they saw the UI, they expect the UI to be there, but when they draw something and their palm can move a little, and then if our UI just follows at that fine-grained detail, that fine-grained resolution, it becomes a little bit annoying because the user wants to touch the location they expect the UI to be, but the UI moves a little. That's why there are a lot of refinements in these projects where we did to make the UI more predictable, like matching what the users mentally would expect for the UI. More details are in the paper, so please refer to that if you are interested in more details. And for the second question, we did the study kind of in a controlled environment in our lab without considering the user's contextual information. But I think that's a very good point for future work. What if we bring this tablet to the users when they are on site, when they're working on their stuff, and how can these type of interaction be more useful when it's deployed in the wild? I think that's definitely more merit future research.
Okay, let's thank our speaker again and congratulations on the honourable